Welcome to Fundamentals of Artificial Intelligence. Today we shall look at propositional logic. In propositional logic, simplest statements are treated as indivisible units, and that makes it fundamentally different from Aristotelian logic. Propositional logic is also called sentential logic or statement logic, since logical relationships are involved between statements or propositions treated as wholes. Let us start our discussion of propositional logic by looking at the definition of proposition. A proposition is a statement that is by itself either true or false. Statements like all humans are mortal, Ram is married, I will pay for the meal are propositions, for they can evaluate to either true or false. On the contrary, statements like come here, why are you crying are not propositions, for you cannot evaluate them to be either true or false. Come here is a command, why are you crying is a question. Propositional logic is a mathematical system for reasoning about propositions and looking at how they relate to one another. Every statement in propositional logic consists of propositional variables, which are then combined via propositional connectives. Every variable represents some proposition. Let us say I want to talk about the day. I would say it is hot. I can use a variable to represent this statement. Then I would have to use another variable to say something like it is humid. If I want to now construct a more complex statement like if it is humid, it is hot, then I need to use connectives. So, connectives encode how propositions are related. We started with two simple propositions, one saying it is hot, the other saying it is humid, and then using propositional connectives I could create a more complex statement like if it is humid then it is hot. Propositional variable represents an arbitrary proposition. We represent propositional variables with uppercase letter. Continuing our discussion about the weather today, we could use a variable symbol like P to represent it is hot and another variable symbol Q to say it is humid. Each variable can take one of two values. That is, the variable can be either true or false. If a proposition is true, then we say that its truth value is true, and if a proposition is false, we say its truth value is false. Let us now look at the propositional connectives. We will first focus on the three logical connectives. The first one of them is the logical NOT, read as not P. Not P is true if and only if P is false. Not P is also called logical negation. The next propositional connective is the logical AND, read as P and Q. P and Q is true if both P and Q are true. Logical AND is also referred to as logical conjunction. The third of the propositional connectives is the logical OR, read as P or Q. P or Q is true if at least one of P or Q is true. Logical OR is also referred to as logical disjunction. The OR that we are talking of here is an inclusive OR. That is, it is true if at least one of the operands is true. We will now look at the propositional connective of implication and thereafter the propositional connective of biconditional. But we will again focus on these connectives in detail in the course of our discussion. So, let us look at implication. If P then Q, this is false when P is true and Q is false and is true otherwise. Implication is also called material conditional operator. We have the biconditional P if and only if Q. The biconditional is true if P and Q have the same truth values and false otherwise. The biconditional connective is also called material biconditional operator. Apart from these propositional connectives, we have two more connectives which do not connect any proposition. They are as if connecting zero propositions. They are the connectives of true and false. The symbol top is a value that is always true, whereas the symbol bottom is a value that is always false. Having introduced connectives, variables, let us now look at what it means to have a sentence or a well-formed formula in propositional logic. A sentence, also called a well-formed formula, is defined as follows. A symbol is a sentence. If S is a sentence, then not S is a sentence. We have not discussed parentheses as of yet, but parentheses are used to disambiguate the precedence of the operators in a propositional logic statement. If I have a sentence S and close within the parentheses, that also is a sentence. Next we have sentences S and T, then the disjunction of S and T, the conjunction of S and T, if S then T, and S if and only if T are all sentences. A sentence in propositional logic can only result from a finite number of application of the above rules. A truth table is a table in propositional logic showing the truth value of a propositional logic formula as a function of its inputs. The truth table establishes relationship between the truth values of propositions and compound proposition formed from those propositions. Let us take a sample truth table to see what we mean. Here is the truth table for the disjunction operator. I have the input values P and Q, and here the P or Q. P or Q is true when one of the operands, either P or Q, is true. So, we have P being true, Q is true, therefore, P or Q is true. For the next statement here, P is true, Q is false, but then P or Q is true. Here Q is true, therefore, P or Q is true. In the last row, we see that P and Q both are false, and therefore, the disjunction is false. From this example, we can realize that truth tables formally define what a connective means, and truth tables can be used for deciphering complex propositional formula. Now, let us focus back on the implication. For proposition P and Q, if P then Q, the implication or conditional statement is false when P is true and Q is false and is true otherwise. So, if we look at this statement, if P then Q, P is called the premise or hypothesis and Q is called the conclusion. The truth table of the implication if P then Q here shows that the only way to get this false is when P is true and Q is false. We want if P then Q to mean whenever P is true, Q is true as well. And the only way this doesn't happen is if P is true and Q is false. In English, a sentence of the form if A then B can have different meanings. Typically, there is a causal relationship between A and B, which is not required in logic. We are often implying more than simply that if A holds, then B holds as well in English. Let us take an example and try to understand this. If I make a statement like, if I earn a bonus, then I will buy a car. The common sense interpretation of this sentence is that the inverse statement is also true. That is, if I do not earn a bonus, then I will not buy a car. Now, let us use some prepositions. Now, let us take a variable P to represent I earn a bonus, the variable Q to I will buy a car, then the statement if I earn a bonus, then I will buy a car could be if P then Q. One needs to realize that the common sense interpretation of the above sentence, that if I do not earn a bonus, I will not buy a car, is not included by if P then Q. Let us look at now the biconditional of statements P and Q, which is denoted as P if and only if Q. It is true if P and Q have the same truth values and false otherwise. The biconditional operator is used to represent a two-directional implication. Specifically, P if and only if Q means that P implies Q and Q implies P. Conversely, if both P implies Q and Q implies P are true, then P if and only if Q is true. Let us look at the operator precedence for propositional logic. We have 5 operators: the negation, the conjunction, disjunction, the implication and the biconditional. Not binds to whatever immediately follows it. The conjunction and disjunction binds more tightly than the implication, and all operators are right associative. Now, as mentioned earlier, we can use parenthesis to disambiguate the operator precedence in an propositional logic formula. So, here is a formula where we have some connectives between x, y and z. Now, until we put parenthesis, it is not very clear what this is. So, parenthesis can disambiguate the precedence. We could have this statement actually saying negation of x implies x or z and y. Now, let us try to translate English into logic statements. and look at the intricacies of the logical connectives as well as implications and biconditionals. In order to translate English into logic, the user defines a set of propositional symbols like P and Q, and thereafter the user needs to define the semantics for each propositional symbol. Coming back to our discussion of the weather today, let us say we use a propositional symbol P to mean it is hot, Q to say it is humid, and R to say it is raining. Now, to make a statement like if it is humid then it is hot, I would simply use the implication Q representing it is humid and P representing it is hot. So, I would write this statement as if Q then P. Let us take a little bit more involved statement. Here is a statement which says if it is hot and humid then it is raining. So, here before I think of putting the implication, I need to realize that I have a conjunction of two propositions, one being hot, the other being humid. So, this one I would write like P, that is it is hot, Q representing it is humid. So, I write the premise as hot and humid and the conclusion as raining R. So, I would write that if P and Q then R. This would mean if it is hot and humid then it is raining. Let us now take a little bit more complex example. Let us use W to represent I will work hard, V to mean there are vacancies, and J I will get the job. Let us try to represent this statement. I won't get the job if I don't work hard. Now, J is representing I will get the job. So, not J would represent I won't get the job. W represents I will work hard. So, not W will represent I don't work hard. But then how do you write this statement I won't get the job if I don't work hard? So, this statement could be written as not W then not J. This is literally saying if I don't work hard I won't get the job. So, if I have a condition where P if Q is there, then it translates to if P then Q. This is very important to realize. If you reread this sentence, I won't get the job if I don't work hard. Actually what I meant is if I don't work hard then I won't get the job, which then clearly shows where I used if I don't work hard then I won't get the job. Let us take another example. If I work hard but there are no vacancies, I won't get the job. Now, in this statement I have I work hard, so that is W. There are no vacancies, so that is negation of V. I will get the job is J, so I won't get the job is minus J. However, one thing to realize at this point is that because the second part of the sentence, that is that there are no vacancies, is a surprise, but is used in English instead of and. But when I am converting it into a propositional logic formula, I would use an and. So, this statement would convert to I work hard W and there are no vacancies, not V, I won't get the job. not j. This is something we need to focus on and look at, that if I have a statement which says P but Q, then I need to translate it to P and Q.